All right, so again, what we're going to look at is, if we look at the D7, it's just going to be the sign bit. We have these guys for magnitude. Now, for unsigned numbers, this is what we have from 0 up to 127, okay? When we get to, for negative numbers, again, D7 is a 1, but the magnitude is going to be represented as a 2's complement, okay? So let's revisit it. You write not the magnitude of the number in 8-bit binary with no sign, invert each bit, and then add a 1 to it, okay? So what we'll have here is, in 2's complement, the minus 128 is represented by a 1, 3 zeros, and then all zeros here, okay? That's minus 128, all right? 127, 126, all the way down to minus 1 is all 1s, and then we go on the positive side up to 127. All right, so this is our representation. This is all I can do in 8-bit arithmetic. Okay? So if I add a minus 128 and I add a minus 2, what do I get? What do I get in base 10? Minus 130. Can I represent that in 8 bits? You can't. Okay? You physically can't. So in that case, we're going to be talking about an overflow situation. All right? All right, so if I take minus 34 is represented internally as, basically you take this, which is going to give me 34. This is the binary, this is the magnitude, represented in unsigned, right? Just there's 34. Take the 1's complement of it. Take all the 1's complements, so just invert all the bits, and then simply add a 1 to it, and that's going to be CCH, all right, in hex, so this is CC, which represents a minus 34, okay? That represents that negative number, okay? So that's the internal representation for it, all right? All right, so let's look up, bring up your studio and just grab a couple of these and we'll see how they're represented here. Let's see how the AVR represents them. Yeah. Should be. Math and Logic. Uh-oh. What were we, Roy? All right, let me wave my magic wand here and go to TU Portal. Sorry about that. I could have swore I put them up right before I came downstairs. Did you guys hear about the USB issue? Take a look, Google the USB problem, you will find that USBs are now going to be that bad for infections. Yeah. Really, really bad. And I can't see why they can't get a fix around it, but this is just, I only know what I read. Anybody leave a USB drive last week? I'm not putting it in there to check it. I'm not. Yeah, STDs. All right. There it is. What are you talking about?
There's no link to...
No attached files.
Huh?
There's no attached files.
Oh, I forgot to attach a file. Sorry about that. I typed the name in, but I didn't attach anything. Ooh, sorry about that.
What's going to be the alternative? Cloud? Can't they just put anything in the cloud too? Like, I got U2's album.
Yeah.
Was that any good? No, I never. No.
All right, do you have it now?
Did you download it, or it's just like? It just showed up on my phone. You can get rid of it.
Did everybody get it? Okay. All right. All right, so let's just run this on the 169.
Gotta refresh.
All right, so we're just going to load up a couple of registers.
What slot?
What number is this guy? This looks like it's number 38. Yeah. All right, so notice that this is the internal representation for -5, which is in FB. DE is going to represent the -34, and 80 represents the -128. Now you will look up here. You won't see any of the flags are affected because the flags are not affected by a load instruction. If I did an addition or something like that with them, then I would start affecting my flags. Okay? So the LDI doesn't affect it at all.
So the V flag goes high if there's 2 complements overflow?
If there's an overflow on the arithmetic.
So if you did 2's complement on 0, 0, the V flag would go high.
If I did a 2's complement on 0, 0, what do you mean?
Like, if you do it like with the neg or the com instruction that does a 1 complement and then adds 1,
Okay.
the V flag should go high.
On 0?
When you add it to FF, the complement of 0, 0.
All right, the complement of 0 is FF, but then when I add a 1 to it, it's going to give me all zeros.
But then it overflows.
It's not an overflow, that's a carry.
So what's a 2's complement overflow? What's the difference?
Well, just hang tight. We're going to get to that right now. That's what this is all about. All right. All right. So, and obviously, I can handle word size numbers. All right. So the word size numbers are basically you're going to go from D0 to D14 is going to be the magnitude. D15 will be the sign bit, and I go from -32,768 up to 32,767. It's just doing 16-bit. Okay, 2's complement. You handle it basically the same way. Okay. All right. So let's get to your question. Overflow problems this is in signed arithmetic. All right. The CPU indicates the existence of it by using the V flag. Okay. But it's up to you to figure out what to do with it, okay? Now, on the Intel series, if I was doing 8-bit arithmetic and then ran into, and I was doing something where on that system, it's called the OF, the overflow flag. But if I ran into a situation there, I could then do what's called sign extension from 8-bit into 16-bit. So if I was doing 8-bit arithmetic, there was a way that I could just simply do it in 16-bit. But you have to be able to take care of that. You have to be able to detect it and take care of it. All right, the result of an operation on signed number is too large. It's just too large, and the overflows occurred, and you got to be notified of when this happens. All right, so if we take plus 96 and add it to 70 in 8-bit arithmetic, all right, I'm going to get this A6 back here, and I'm going to notice that the V flag and the N flag are both raised. The V flag is raised because it is an overflow. I'm doing 96 to 70, which cannot be represented in 8-bit arithmetic, because now I'm going past 127, okay? And the N flag is raised because I have an A sitting here in R16. The most significant bit here is a 1, so that gives me that N flag, okay? So what this is telling me is that that's a negative number. Well, it can't be a negative number because I'm adding 2 positive numbers together, okay? We're going to get overflows only when you're adding 2 numbers of the same sign, all right? If I have opposite sign addition or subtraction, you can never get an overflow because the magnitudes, it'll always keep you inside of there, all right? It'll always keep you inside of that 8-bit. So the only time it can happen is when I have 2 of the same sign numbers that I'm adding or subtracting, okay? I mean, that's basically how that works, all right? So in the above example, it's 96 is added to 70, and it gives me the CPU's telling me, if I'm doing this in 2's complement arithmetic, this is telling me that it's -90, all right? And the reason is that the result was more than the 8-bit register R16 can effectively handle. And so it's like all 8-bit registers, R16 can only be represented up to a plus 127, okay? So this informs me that the result of the signed number operation is wrong. Okay, it just can't be done in that arithmetic. All right. So the conditions are the overflow flag will be set if any of these 2 conditions. So this is just basically taking that into consideration, the addition of 2 of the same sign numbers, whether positive or negative. All right. And effectively, what we're doing here is if there's a carry from D6 into D7, but no carry out. Or if there's a carry from D7 into the carry, but no carry from D6 to D7. So that gives me any of these two conditions will raise that overflow flag up. So in other words, the overflow flag is set to 1 if there's a carry from D6 to D7, but no carry out from D7 into the carry flag, all right? So that basically says there's a carry from both D6 to D7, and from D7 out, and that says that you're okay. We're good. The overflow flag will not be set, all right? So if you look at the addition here of plus 96 and 70 in binary, so you just write down the plus 96 in binary, write down the 70 in binary, and you start doing the addition. 0 and 0 give me 0, 0 and 1 give me a 1, 0 and 1 give me a 1, 0, 0 give me a 0, 0, 0. Then I get down here. I have 1 goes down here, 1 and 1. So now I'm operating on D6 here. 1 and 1 give me a 0. There's a carry from D6 into D7. When I add these numbers together, I get a 1 here. There's no carry out. That tells me that the overflow flag is going to go off. Okay? So I have a carry propagating through D6 into D7, but no propagation out. Okay? In that case, obviously you'll get the V flag will be up. I have an overflow. The N flag will get set up because I have just a 1 there. Anytime I have a 1 sitting in that 7th bit or the 16th bit, that thing will go up. Okay? And the carry flag is obviously set to 0 because there's no carry going from D7 into the carry flag. All right, so if we take this example, obviously minus 128 and minus 2 is going to give me minus 130, which can't be represented by an 8-bit signed arithmetic. Okay? So in this case, the minus 128, I'm just loading it up in hex here as 80. The minus 2 is getting loaded up as FE. We add those guys together. So you simply put, and obviously I'm going to get a 126 out of this result. The N flag is going to be 0. All right, so if you look at it, there's my minus 128 in binary. There's the minus 2 in binary. Adding them together gives me, when I start adding them up, just give me the zeros to zeros. I've got the 1 and 1 here, 0, and we have the V flag is going to be set equal to 1. So it's obviously an erroneous result, and the CPU basically says, you got an issue here, all right? The N flag just gives me the sign of the corrupted result, not the sign of the real result that I was asking you earlier. Okay, the sign flag, we'll discuss what the difference between the sign and the N flag are. And you can see it here. In this case, I do get the sign flag, the V flag, and the carry are set. The N flag is not set, okay, because I have deleting the 7th bit is sitting there. All right, the add instruction, there's two different conditions, all right, that can happen. Either the operands have the same sign or the operands are different. When we add two numbers with different signs, the absolute value of the result is smaller than the operands before executing that thing. So we know that the numbers, when they're the same sign, you'll never have a problem, okay? I mean, opposite signs, all right? With different signs, there is no issue with that, all right? So the overflow definitely can happen when the two operands with different signs. It only happens when you have the same sign, and in this case, the absolute value of the result is larger than the operands before executing that add instruction. That's going to give me an overflow, okay? So it's possible to write the result that's too large for a register and can cause an overflow, all right? And you add the two numbers with the same sign, the result should have the same sign too, obviously. Two negative numbers, give me a negative number. Two positive, give me a positive, all right? So if we add the two numbers with the same sign, the resulting sign is different. We know that an overflow has obviously occurred. Two negative numbers, if my result is positive, it can happen. Two positive numbers give me a negative number, can happen, all right? So we know that there's an issue there. So this is exactly what the CPU tests. There's a way I can set this up, or not, I mean, there's a way we can set this up. And basically it's this. If I'm doing the following add instruction, now again, you're only going to be worried about bit number 7, so we're doing an add. Let me get a little better pen here. RD, comma R, R. All right, so that's how it's set up. Now what we're going to look at is bit number 7 of the destination register gets added with bit number 7 of the other adding register, and the resulting bit number 7 is complemented. So these are all ANDed together. They get ORed with the destination register's 7th bit complemented, ANDed with the 7th bit of the other register 7th bit, and the resulting 7th bit. That is the test for the V flag. That handles all the signs, all the numbers, all the magnitudes, and everything. So that is how the V flag is physically set. It has these already in there, and it does the ANDing over here, ORs them together. That's going to give me a 0 or a 1 here. 0 is no overflow, 1 is an overflow. Okay? So that's basically how that guy's set up. That clicker. All right? So again, destination register, here's the other register that I'm adding to, and then the resulting register will be in or in the destination here, so that it simply has these 6 bits, and it performs that logic operation. Anton.
What's just the R7?
This is going to be in the resulting. This is RD. I got like R16 here. This will be R17, let's say. This will be what's going to go into, like if I had R16 here, it will take R16's. This would be R16 7th bit, R17 7th bit. When the result is performed, when the addition is done, that register, R16, is the destination. It's going to take that 7th bit that occurs there and perform these ANDs.
All right, so if there's no little R, little B, that's where the destination.
That's the destination register's 7th bit. Okay? All right. All right, now what I'd like to do is, this is just an example of -5 and -2. -5 is represented with this binary number, which is an FE hex. -2 is FB. We know that we can get, we're going to get -7, which would be represented as F9. So when you add these guys together, you physically, here's my -2 in binary, the -5 in binary. When I add them together, the V equals 0, the N flag is 1. Because the 7th bit is set here, the V flag is set equal to 0, we're fine. Everything's, life is good, all right? Just ducking, that's just, here you could see that the V flag isn't set, the N flag is definitely set because the 7th bit is high. And we'll get to why this other S bit is signed here also. Okay, we'll talk about that shortly. And just to give you another example of +7 and 18. Again, same sign. I forgot to put the plus sign inside of there, but so we get 25, and it's just, again, just running that test on the V flag gives me this guy here, okay, which will be a +25. All right, so the summary, as we saw in the last examples, that we conclude that in any sign number addition, the V flag indicates whether the result is good or bad. Okay, so you just got to test the V flag. All right. V equals 1, it's erroneous. You got to extend it to either 16 bits or you got to go to higher multi-bit precision. Okay. If it's 1, everything's great. Okay. So you can state basically pretty much guaranteed that in unsigned number addition, the programmer must monitor the carry flag, and in signed addition, you look for the overflow. Okay, so when you're doing 8-bit unsigned stuff, just look for what's propagating into the carry. That will tell you if you're now going out of the numbers that you can use for unsigned arithmetic. All right. And there's also in the so when you can test this, for unsigned arithmetic you can branch on a carry set, you can branch on a carry clear. That allows me to do branching. So if I do come into an issue with unsigned arithmetic, I can use the branch on carry set and the branch on carry clear to handle that. Okay. There's also a branch on the V flag. All right, if the V flag is set, so these are built-in tests to take care of the overflow issue. All right. So there's also 2 branches for the N flag also, which are BRPL and BRMI. Okay. All right, we're going to do a little in-class assignment here. All right. You 3 guys here are going to work on this problem. All right. Huh?
AMD or
Just A. A. And then you're going to come up and talk about it. All right. You guys got B. Okay? C? All right. Now, let's go over here. You guys got D. All right? Hex. All right? Two guys in the back, F. All right? You guys in the back, G, you three. Three of you work together. Or no, how many are do I have enough here? Hold on. Let me make sure everybody gets a problem. You guys have one, D, right? All right, you don't have one? Was H the next one? All right. H. All right. I. All right. J. You three guys work on E. And you guys work on G. All right? I want you to do it by hand. All right? So convert. When you're given the decimal numbers, you have to convert them to their two's complement. Use the calculator, whatever, but I want you to work it out by hand. All right? And tell me what happens to the V flag and the N flag. All right?
15 is 1, 1, 1, 1.
In binary? Yeah. Well, it's 8 bits, so 0, 0, 0, 0.
Work together. Chat it out. And when you all of you come to a consensus, come on up and grab a pen, and we'll work it out on the board. All right? And if you want to verify it, just run it in Studio. But I want you to go through it by hand to make sure that you understand what's going on here. All right?
You gotta do it here.
Did you ever get the 3D print?
Yeah, I got somebody to do it, but we have to change the design because he's using the maker, not the printer. And your design is,
Oh, and they want us also to split it in two.
yeah, that's
Yeah.
what we're trying to do now.
All right. When you get it done, let me know, all right? Anybody got it yet?
R16 tells me that it's 3, and that's what we expect with no V flag. Well, I mean, you talk to the V flag can't go higher for that.
You got it?
Got it.
Catch a fly ball. All right, somebody come up and put it up. As soon as you get it, come on up, grab a marker.
And that should give you
When you come to a consensus and you think you got it right. And then you'll do it, Tyler, then you can do it in Studio 6, all right?
Wait, I thought,
What's up?
so the V flag turns on when you do an operation on numbers that are the same sign, right?
V flag can never be set, right, yes, it is set on numbers that are of the same sign. Which one do you have?
I have J.
J. All right, 3B and E2. We're doing 2's complement arithmetic. Is the 3 a positive or negative number? Write it out. What's 3?
Oh,
3B,
never mind. It's
3B and E2.
positive.
Yeah, that's a positive number. 3B is a positive number. How about E2?
Oh, that's negative.
That's a negative number. So you're adding a positive and a negative number here.
Oh, I didn't. Okay, they're twos.
You got to get thinking. That's the reason I put this exercise up here. I think everybody's like, 2's complement, I know it. Come on. You're adding, in this case, a positive number. This case is a positive number to a negative number. All right? What about in this case? Negative number to a negative number. Could be an issue here. This case. Negative to negative. Here. Negative to negative. Negative to negative, but this is in decimal, so you got to convert it over. Okay? All right, so what do you have up here, Tyler?
Well, we have 15 minus 12, and you know if you're subtracting a number, you can pretty much just add the 2's complement. So I form the 2's complement of negative 12 over here, you get this. And then when you add them, you get a carry, because the red term flows, so you get carry equals 1. There's also a carry bit from the 3rd to the 4th.
Okay.
H flag would go high. The most significant bit 0, so then the S or the N flag would also be 0.
0. Right.
And you can't get the V flag if you're adding different sign numbers.
Correct. Yeah. All right, so very good. So they get a 3 out of that one. All right. Which is right. I mean, it's just. Okay. Anybody, you guys ready? All right, come on up. Who's next? Anton? Jacob, you guys ready? All right. All right. Why don't you go up on the left-hand board over there? How about you guys? You guys come to a consensus here? Huh? Amigon? Yes? Got it? How about you guys? You all right? All right. Pick somebody to come on up. You guys? What do you got?
We got 190. We add 0 083. Got
Carry flag is set.
carry flag and sign flag. Carry flag because we have a
What are the numbers? Give me the numbers in
decimal.
decimal.
Oh, we are converting.
All right, convert them over. Okay. How about you guys? You all right?
Yeah, okay, we're just converting decimal.
Okay, yeah, convert them to decimal also if you have hex numbers, all right? So you guys got to convert them. Yeah, like, that's how you're going to check it, right?
Yeah.
Yeah, you got to check it. How about you guys? You all right? Michael, what's the matter? Forget your 2's complement? What's that? Got to freshen up because guess what? Friday's coming in a hurry. We don't want. That's why I'm doing this. Really, to just all of a sudden it's like, uh-oh, I got to review this. All right. All right, go ahead, Rachel. Explain what you got up there.
Okay, so ours was 126 and 127, and because it's 2 different side numbers, we know that B is not going to equal 1 automatically. But this is 126 to find negative 127. We took 127, found the complement, added 1. And there's no carries on any of these. It just ends up being FX. And the 8th bit is 1, so we know it's negative, and because of the sign arithmetic, X is also 1.
So in decimal, your result is -1.
Minus 1, yeah.
Yeah, very good. Okay. All right, go ahead up. You can erase the right there. All right, Anton, tell us what's going on there.
We had negative 123, negative 127, and you know that it's going to be higher than negative 128, and because there's a carry into the 8th bit, and there's no carry from 6 to 7 that is high, and there's the n equals 0 because the 7th bit is low.
Right. Everybody get that? You can see it here again. He's got 2 of the same sign numbers. They're both negative. Immediately, the 7th bit, I'm going to have a carry out of the 7th bit on this. All right? So now I look for, was there a carry coming in to 7 a carry from D6 to D7 and the carry out. So that's how we're testing it here, okay? That's how you test it. And immediately, as Anton said, that's going to give me a V equals 1, okay? You guys ready? Go ahead, take the left board. And you three guys can work together. I mean, help each other. That's the whole idea of this. It's a walk down memory lane here, all right? You guys almost ready? Well, then, this will tell me.
Because we've got 9D for the summation,
Yep.
as we have here. So app A.
Verify it by hand also.
Yeah, is also verified by.
Well, where's the numbers? Where's the hand? Where's the calculation?
A plus 3, it's D. F plus A, it's 9 with a carry.
Okay.
So
Now, would I like you? Did you convert this to make that
it's minus 6.
minus 6
And this is
minus 93?
And
So
this
you're
is
going to get 99.
99, which is 0, 1, 9D. This one is the sign bit. This is 9, this is D, which is minus 99.
So 9D is minus 99.
1, 9D, it's minus 99. Yeah, 9D is.
That's what I'm saying. Which is which?
Yeah.
We're doing 8-bit arithmetic, so that's all you're working
That's
with.
it. But the last
To
one,
take the choose complement of this value, and then you get minus 99.
Show me it.
Minus 99.
Do it.
yeah, it is. Because this one is 0, 1, 1, 0. 0, 0, 1, 0 plus 1, 0, 1, 1, 0, 0, 0, 1, 1, which is 4, 5, 6,
6, 3.
6, 3, yeah. This is 6, 3.
Yep.
Do you have a different marker?
Oh yeah. There's a. Oh yeah. Don't use the green one. Yeah. Here.
It's not working. I just changed it from 2 to 17.
Oh, that's okay. But here, I got to get rid of these. Yeah.
Do you want this red marker? I have some darker ones.
I still want a doctor.
This one works. That'll work. Is that green one? That's green one's dead, right?
Basically, yeah.
All right. All right. Go ahead. What do we have on the right? 25 and minus 34.
Yes, to represent the, I need to add these two numbers. So to represent the minus 34 in hex, I need to flip first the bits, and then I need to add one. So this is the result to perform the addition. And then I will add these two numbers. I get this. So look, the D7 is 1. So the N flag will be set. And also the C0 and the V is 0.
You have the V flag as 1 or 0?
0.
0. Yeah. Okay. And your answer is minus 9.
Yes, minus 9.
Minus 9. Okay. No. Let's you. Don't say that this is equal to this. This represents just a minus 9 decimal.
Yes.
Yeah. You don't need hex. See what I'm saying?
Yeah.
Yeah. So take away the H.
Yeah.
you know what? You got to do either D or base 10, one or the other. All right, because that's yeah. Okay, go ahead.
Our numbers were negative 120, negative 10. If you do it just normal, your brain should be getting negative 130, but that doesn't work quite so well in the computer because you do negative 10, negative 120, then comes out as 126 with your V flag as 1 because you have your carry coming out of your D7, but you have no carry coming into it.
No, nothing in the D7, right?
Yeah.
Yeah. All right, cool. All right. You guys ready?
Yep.
You guys ready? You two ready? Here. Come on. And board's up there waiting on the right there. If you don't have it, don't worry about it. We'll work it out on the board. That's the whole idea here. All right, well, we know the answer is what?
Minus 106.
106, all right?
Minus 150.
Yeah.
because of the
All right, so
over. We have an over.
there shouldn't be an overflow here because it's not past minus 128. You should not get an overflow here. It's okay, let's work it out. When they get done on the board, well, everybody's going to help you here. All right, that's the whole idea. But we have to go back and revisit your two's complement. Okay? Yeah. All right, what do you got? Oh, another. All right. Miss Rachel, can we borrow your red marker? Thank you. Oh, all right. He's got his. Oh, all right. Yeah. At least I'm knowing which ones are alive and which ones are dead here. We're taking your picture, my friend. We'll save this one so we can put it up online. Smile, too, all right? Has anybody been going online and looking at the videos? No? Not much? I don't know how much. Because you should get this other software it'll capture what's going on the monitor too, on the podium. Can't see the Temple Tito.
It's there.
It's there. I know. Tony, how you guys doing? Working on it? All right. Yeah. What's up, Jim?
When we did the 25 and then 34,
Yeah.
you know how it gave us F and 1 technically because it was 1 1 1 0 0 0 1.
Okay.
So it's F and 1. So does that automatically know that it needs to store to?
That's the result stored in two's complement.
So it's F1 stored in 2's
Yeah.
complement. So we're gonna
What was the number? Minus
negative 9.
minus 9. Yeah.
So it's gonna stay as F1.
It's going to stay as that.
So when I do that and I
The computer doesn't know that. I mean, it does, but you've got to handle the issues with the additions, all right, and
it'll
subtractions.
stay in the register as.
Oh yeah. That's, until you overwrite it. One, Anton.
So there you say the E2 is negative. That's only negative because you told us it was negative, right? Otherwise, that would be a positive.
Everything is in two's complement form here. Everything.
But C, you said negative 34H is negative.
Which one now?
Like number C.
C.
You said negative.
Well, well, this is in hex. You know what? I think I made a mistake. I should have had decimal there. I can't do this. You're right. Everybody look up. There is a mistake here, and Anton picked it up. Plus 25 hex. There is no such thing. I meant to have these as D's here, decimals, or just as decimals, because there is no such thing as I can't say a minus 34 hex. You see what I mean? That makes no sense. The only way a hex number has the sign is built into the 7th bit. You see what I'm saying? It's built into the 7th bit. So this makes no sense. You see what I'm saying? No sense, because everything's on the 7th bit here. All right, so if we look at this, if these are in hex, I can't have a negative there. All right? How we doing on the clock?
43.
Oh, all right. All right, so what do we have on the right-hand side here? 3B, E2. What do we get?
So you got 3B plus E2. You take the 2's complement and you have a negative plus a positive. So since the signs are different, B bit is going to go to 0.
Okay.
And since there's no carry beyond D7, your C is going to be 0 as well.
Okay. Is that right? Verify it? Okay, good. You're on candid camera. When does that see them? Good. Eh. All right, go ahead.
So we've got 0x5a plus 0x83, which is minus 6 plus minus 93.
Now this could give you an overflow because you got two of the same signs here. All right, let's see what happens.
But does not give us an overflow because there are two carry bits here. One is the carry out, and one is the carry bit from 6 to 7. So 1 XOR 1 is 0. So there's no overflow. And when you do the summation, you've got 1 here, so it's the N flag. N flag is 1. And the sign flag is N XOR V, and so 1 XOR 0 is 1. So sign flag is 1, A flag is 0, and C flag is 1, because when we add here, we have carried out.
Yeah.
And the last, the result is.
So 9D gives me minus 99 decimal.
That's it.
We're good. Good. If you notice, just hang tight. He has the expression for the sign flag. It's the you take the overflow flag and you exclusive OR it with the N flag and the V flag get exclusive OR. That's going to give me what the sign is. Okay. Now you notice here, the result is not overflowed. It's a negative number, and that's telling me the result of the sign. All right, which is okay. All right. Yeah. Now again, if you don't have it, we're here to help. All right. So the idea is let's think it through. You guys ready?
They did ours. You had us do E.
Oh.
They did ours too.
Did you guys verify?
Yeah, I got the same results.
Okay. All right. Minus 99. Okay. Yeah. Which one? Here? Right here? Why? The V flag is going to be equal to 0. Okay. All right. The V flag is you're going to have the carry out because you have the V flag is set. It does an exclusive ORing operation on the carry that comes out of bit number 7 and the carry from 6 into 7. You exclusive OR them two together. That's physically how it's done. It takes those two flags, exclusive ORs them. In our case, when you exclusive OR 1 and 1, what do you get? All right, because it's exclusive ORing. Right. Okay. You got it. Everybody all right with that? You got it? Good. Captive audience out in the hall. All right. And I have, on the slide right after that, I have what's the difference between the S and the N flag, so you can look that up. All right. Is this a little more instructive? I think it's a little bit better than, all right? I like to keep, we're going to be moving over there soon, next week. You're going to get a box of parts in lab this week, get some hardware, start playing around over there, all right? So you'll need to bring your butterfly boards, all right, to class now, all right? Oh, and do me a favor. These are in little tubs. I know you'll be walking around campus with it. Last year, we had a little issue in Paley Library. Somebody had their little box of electronic stuff, went to the men's room, left it next to the sink. Somebody comes in and says, bomb. They evacuate Paley Library. Police come, and I see a mysterious electronic device. I get the text alert. I'm like, somebody left the tub in Paley Library. And I came to class the next day and I said, who was the one in Pele Library? And the one guy goes, oh, it's me. So make sure. No, it happens. You know, I mean, at this day and age, you got to watch it, all right? So. It's just, yeah. I mean, it's, yeah. I mean, when I go down to Lunabots in Florida and I go through the airport, it's like every time I'm like, I got to declare I'm carrying all this parts and everything, and you know. All right, so we good to go? 49. All right, let's help this guy out up here. What do we have here?
Is that a 90 thing? Yeah. Yeah, no.
Yeah.
Alright, we convert
Oh.
the numbers into two complements. We get this addition. So if we notice we have
All right, so these are the two numbers in their two's complement representation, right? All right, so let's go. Let's go through the bits.
alright, we have
0, 0.
0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 0, 1, 1, 1, 0, carry on. 1, 1, 0, there's a carry. 1, 1, 0, 1, and there's a carry. The carry flag is going to be
So you have a carry coming from bit number 6 into bit 7, and you have a carry come from 7 out. All right. So why is this equal to 1?
because we have
Is there an overflow here? And there's no overflow on this.
I thought overflow was from
You're exclusive ORing the bit 6 to 7 and the carry out. So you an exclusive OR. You have a 1 here, right? And then I have another 1 coming out.
Yeah.
So if I have a bit here going into 7 and a bit coming out, then V is going to equal 0.
Oh, okay.
It's an exclusive ORing operation, as we mentioned over here. It's an exclusive OR. And you shouldn't have an overflow because this is
Yeah, I was
minus
thinking,
106.
I was thinking like if there is a carry from D6
All right.
to D7.
We're good. All right, have a good one, gang. See you on Wednesday.